dual-phase steel under ultrasonic fatigue loading for low stress amplitudes below the conventional fatigue limit of the material. At first, I will present a brief introduction and some explanation about the material under study, and then I will present the experimental results obtained in this research, including the self-heating diagram and the intrinsic dissipation measurements, and finally I will present a brief conclusion. Ultrasonic fatigue loading is an effective tool to do high and very high cycle fatigue tests. I will not explain more because we had enough explanations during the invited lectures, and I just mentioned that we can use the heating effects induced by the high frequency to study the fatigue behavior of the material. Actually, this work is not directly related to fatigue crack initiation rupture, but the heating measurements can help us, which can help us to study the fatigue behavior of the material. We are going to do some studies on thermal response of a dual-phase steel under ultrasonic fatigue loading, just for low stress amplitudes. There are some similar studies for conventional fatigue limits, study the fatigue behavior of this material under conventional fatigue loading, but here we concentrate just on ultrasonic fatigue loading. The material under study is the dual-phase steel. As you can see, its microstructure in this board, in this picture. It consists of hard martensite islands dispersed in a soft ferritic matrix, and you can see the mechanical properties of the material in this table. It was received as sheets of 3.6 millimeter thickness, and it contains of 15% of martensite. In order to do the ultrasonic fatigue specimen and fatigue tests, we designed the fatigue specimen as you can see here in this picture. It's an hourglass-shaped specimen with the dimensions shown in this picture. It was designed in such a way that the free resonant frequency of the specimen in the first longitudinal mode is 20 kHz, equal to the frequency of the testing machine. So here you can see the experimental setup used in our study, the ultrasonic fatigue horn, the hourglass-shaped specimen, and also an infrared camera that we used in order to capture the temperature on the surface of the specimen during the test. In order to study the self-heating behavior of the material, we did successive fatigue loadings with increasing the stress amplitude. All of the tests were tension compression with the ratio of -1. And there was a gap of around 10 minutes between two successive steps in order to assure that we start in the equilibrium state. Moreover, as I mentioned before, the maximum stress amplitude in our case is around 247 megapascal, which is under the fatigue limit of the specimen, which equals to 250 megapascal. And each block of loading consists of 10 to 7 cycles. So we did the fatigue test at each step, and we captured the temperature on the surface of the specimen, and also after stopping the load, we continued the measurements of temperature to capture the cooling part of the specimen also. Here you can see the temperature evolution for one of the loading steps as an example with the stress amplitude of 208 megapascal. As you can see, there are three main stages. In the stage 1, the temperature increases and then it reaches a steady state at stage 2. This steady state corresponds to a balance between the mechanical energy dissipated into heat and the heat losses through conduction and convection. And afterwards, in stage 3, we can see the cooling of the specimen. after stopping the load, and we will use the slope of the cooling just after stopping the load in order to measure the dissipated energy, as I will explain later. And here you can see the temperature fields on the surface of the specimen obtained by infrared thermography. As you can see, the temperature is homogeneous and symmetrical with the maximum value which is found in the center of the specimen. And here in this picture you can see the temperature increase during cycling for different stress amplitudes. And it's obvious that by increasing the stress amplitude, the steady state temperature has increased. And in the next step, we measure the net temperature increase for each loading step using this relationship, T steady state, minus the initial temperature of the specimen, as shown in this figure. And it's represented by theta F. As you can see, by increasing the stress amplitude, the theta F has increased, and this diagram is called the self-heating diagram for DP600, still under ultrasonic fatigue loading. As you can see, we are limited to low stress amplitudes, the maximum of around 247 megapascal. Afterwards, we use the obtained diagram of theta F and the previous measurements for temperature evolution after stopping the test by using this simplified heat diffusion equation developed by Boulanger and his co-worker, as shown in this relationship. In order to measure the dissipated energy, the intrinsic dissipated energy shown by D1, here in this equation, rho is the mass density, C is the specific heat, theta is the temperature increase shown in the previous slide, and tau is a time constant which represents the thermal exchanges between the specimen and the environment. And in order to measure tau, we use the slope of the self-heating diagram, the temperature evolution diagrams, just after stopping the test. And we obtained this diagram for changes of theta for different stress amplitudes, for tau, sorry. So as you can see, tau decreases by increasing the stress amplitude, and finally it reaches nearly a steady state. Therefore we can use the value of tau for each stress amplitude, and just by using this equation we know theta also, so we can measure the dissipated energy for each stress amplitude. Afterwards, by dividing this dissipated energy by F, which is the number of cycles, we can obtain the variations of mean dissipated energy per cycle versus stress amplitude for our material under ultrasonic fatigue loading. And the important result is that in our case, the dissipated energy per cycle is a quadratic function of the stress amplitude. So if we consider the cyclic loading with the stress amplitude of sigma A, considering the inelastic material, behavior or the inelastic material behavior using the Kelvin-Voigt element, it's well defined in the literature that we can measure the dissipated energy per cycle by these two relationships in each cases. Here, mu and eta are material parameters representing the elastic and viscous moduli of the material. We can see that in both cases, if we assume that eta and mu are constant, in both cases, D1 will be a quadratic function of sigma A, which is inconsistent with the results we obtained in our experimental researches. So, when eta and mu are constant, we can say that the internal state of the material is not changed because they represent the microstructural state of the material. So, based on these results, we can say that in our case, for low stress amplitude fatigue tests, no strong change occurs in the material internal state. So the question is, what is the heating mechanism in this case with no strong change in the internal state of the material? It's well known that for BCC metals, there are two major deformation modes based on the transition temperature as defined schematically by Mughrabi and his co-workers in this diagram. You can see that below the transition temperature, we are in low temperature regime in which screw dislocations are immobile and edge dislocations move to and fro in a non-hardening, quasi-recoverable manner. In contrast, for the temperatures more than T0, which is the transition temperature, we are in the athermal regime in which screw and edge dislocations move with the same velocities, and moreover screw dislocations can cross sleep. So in this regime we have high amounts of dislocation motions, and the plastic string can be localized in slip bands also. So based on our experimental observations and also based on the recent results of Fabier and her co-workers for alpha iron, we concluded that in our case the material deforms at low temperature regime. So the dissipation comes from the to and fro motions of edge dislocations in a non-hardening quasi-reversible manner. So in this work, we obtained the self-heating diagrams for our material, the DP600 steel, under ultrasonic fatigue tests. We observed that at low stress amplitude, the dissipated energy is a quadratic function of the stress amplitude. Moreover, we concluded that there is no strong change in the internal state of the material, and deformation occurs at low temperature regime. And finally, we observed that the to and fro glide of edge dislocations can be considered as the main dissipative mechanism in our case, with no cyclic hardening. Thank you for your attention.